Now, the next speaker is Georgii Riabov from Kiev, Ukraine.
First of all, I would like to thank organizers for the possibility to give a talk on this conference. In this talk, I will discuss flows of mappings and bifurcation points in these flows. I will work in a locally compact separable metric space. Without loss of generality, we can assume that the metric is complete and all bounded sets are relatively compact. By a flow of mappings of this space, I will understand a family theta indexed by two time parameters s and t. So each theta st is a mapping of M. I will consider only continuous in T mappings, and theta ss of x is equal to x. So this function can be seen as a trajectory of a point in the flow that occupied x at time s. And by a flow property, I will understand this equality. So if we take moments of time rst, then the composition of mapping theta rs and theta st is equal to theta rt. The standard source of examples of flows are ordinary differential equations. Let's consider just a d-dimensional Euclidean space and Lipschitz coefficient, and consider the Cauchy problem. One, if theta sx is a solution of this problem, then it is well known by existence and uniqueness theorem for ODEs then that it is a flow of mappings of RD. Actually, it is a continuous flow of homeomorphisms. Now let's do a very simple thing. Just choose a sequence of trajectories from the flow. So we fix some sequence of starting times Sn and starting positions Xn, and consider trajectories from the flow that started at Sn, Xn. Then we get a sequence of continuous functions. And the flow property implies that if two functions in this sequence are equal at time s, then they will be equal for all times t greater than s. So 2 is a simple consequence of the flow property. And I will be interested, broadly speaking, in the converse problem. So assume that we have a sequence of functions in M, continuous, and assume that this sequence satisfies 2. The question is it possible to inscribe this sequence into a flow of mappings? I mean, can we find a flow of mappings such that this flow preserves functions Fn? I mean, theta st of function phi n of s must be equal to phi n of t. So this is exactly the condition that phi n actually is a trajectory from this flow. More, I will be interested in how regular this flow can be made. The approach I will take is we have a given sequence phi n. We will assume that the starting times and positions is a dense set in times space, and we will try to define the flow as certain limit points of this sequence. So we will develop some approximating procedure that allows starting from a sequence of continuous functions extended to a family theta sx, and we will study the question when this family is actually a flow. The motivation to this problem came from theory of stochastic flows. Let's consider the stochastic differential equation. Again, it has Lipschitz coefficients, and W is a Brownian motion. So we can consider the Cauchy problem 3. And also it is known that there is a unique solution to this problem. However, uniqueness now is understood with probability 1. It means that if we have two solutions of equation 3, then they coincide with probability 1. As a consequence, if we fix Rs and X, then this equality holds with probability 1. However, the exceptional set, so the set where the set on the probability space where this can fail, it depends on R, S, and X. So we have uncountably many zero sets. But since there are uncountably many, in their union can be a large set. So it is actually a subtle question. Can we put all this into this event? So can we find such solutions to the problem 3 in such a way that it is actually a flow of mappings? And this problem has a positive solution. So one can find a family I denoted theta prime such that it is a solution of equation 3, and it is really a random flow of mappings. In fact, these mappings are homeomorphisms, and they are continuous in S, T, and X. This fact is important for theory of stochastic flows because it allows to use tools from ergodic theory and dynamical systems to study stochastic flows and their asymptotic behavior. And actually, the way, one of the possible ways to prove this theorem is to fix a sequence phi n of solutions of 3 that starts from a dense set, and then recover theta prime by some approximating procedure. However, not all interesting stochastic flows they fall into this framework. Actually, a lot of do not. I just mentioned a few examples. One can consider stochastic differential equations with discontinuous coefficients. The famous Tanaka equation, dxt equals sine of x dw, where w is a Brownian motion. So it is known that this equation doesn't have a unique solution. Another example is the Aratia flow. The Aratia flow describes actually uncountable system of Brownian motions that start from all points in time and space, and these Brownian motions move independently before meeting and coalesce at the meeting time. This flow cannot be described by any reasonable stochastic differential equation. And actually, there are also interesting stochastic flows on more complicated locally compact spaces, not just Euclidean spaces. Okay, so this is an illustration of the what happens in the Aratia flow. So on the first picture, we see 3 trajectories from the Aratia flow. 2 of them started at time s. They have met before time t, then they coalesce into one trajectory. And second picture is one mapping from the Aratia flow. So this flow produces a flow of piecewise continuous mappings. This shows that we cannot expect some continuity in S and X of this flow. Okay, so to realize our approach, we need the proper notion of convergence of continuous functions. Let me introduce the space of path. So X is a union of spaces of continuous functions that start at every moment of time. So this is a union of continuous functions from S infinity to M and union over all S. So every element of this space, it is a continuous function. It has the starting time, and we can extend it to all real line, just defining it as a constant before its starting time. Then, with respect to metric D, this space is a complete separable metric space. So this metric, it captures convergence of initial times and uniform convergence of functions on segments. Now, I will need one technical result. This is a lemma about choosing a measurable selection mapping. So if X is a complete separable metric space, then there exists a Borel measurable function that acts from sequences in X into X in such a way that for any relatively compact sequence, mapping L maps it into its limit point. This mapping can be constructed as follows. If the space is compact, then actually all sequences are relatively compact, and the mapping can just choose one limit point in a measurable way. One possible approach is to fix a dense sequence and by dm define the upper limit of distances to every point zm and choose a subsequence that converges to its limit. In this way, we will get a measurable selection mapping for the compact space. And in general, every complete separable metric space is homeomorphic to actually to a G delta subset of some compact space, and we can get a measurable selection for X using a measurable selection for T. Okay. Now, a sequence of continuous functions phi n will be called a skeleton if it satisfies three conditions. If two functions are equal at time s, then they are equal at all times t bigger than s. Their starting positions are dense in the product times of time and space. And the third condition is that if we take a compact set L in the product of time and space and consider all functions that at some point visited this set L, then this set of functions must be relatively compact. And the theorem is that there exists a measurable mapping that takes a skeleton phi, and for each points s and x, it returns a continuous function that starts from x at time s and is such that it preserves trajectories of the skeleton. This mapping is constructed using the measurable selection L, and it is constructed as follows. We choose an approximating sequence of functions from the skeleton for each point S and X, and define theta as its limit point. Then the assumptions on the skeleton imply that this mapping is the needed one. In fact, let me explain why this mapping preserves trajectories of the skeleton. So if X is equal to a point on the skeleton, then the approximating sequence NSXK is stationary. I mean, it is just a constant after some k. Indeed, we define this sequence nk as the index of the first trajectory of the skeleton that was at some fixed distance to x. But if x is already on the skeleton, then this sequence nk will just be will be equal to the same value after some point. And since measurable selection returns a limit point, it must exactly return the trajectory from the skeleton. Okay. Now we can define a family of mappings theta and ask ourselves, will it be a flow? There is one case when it will be a flow, namely if after for any time s and any x, after some time after s, this function theta s just coincides with the trajectory of the skeleton. Then we will get a flow, and it is a simple consequence of the property that theta preserves trajectories of the skeleton. And this situation appears when the skeleton possesses the so-called instantaneous coalescence property. It means that if we fix 2 times s strictly less than t and consider all functions, all values phi n of t for functions that started before time s, then we will get a locally finite set. So for this, in this case, actually, this lemma holds. So if the skeleton possesses the instantaneous coalescence property, then we get a flow. This result is actually applicable for Arakia flow that I showed in the beginning, because it is a flow with the instantaneous coalescence property. Okay, but if this property fails, actually theta may not be a flow, and this is because of it can have so-called bifurcation points. I will define them in the following way. So kst epsilon x, it is the closure of all trajectories from the skeleton that were in the epsilon neighborhood of x at time s. So it is a compact set, and we can intersect these sets in epsilon. Yes, so we send epsilon to 0, and in the intersection we get a non-empty compact set of continuous functions. Actually, this set contains our functions theta. Now, nu is the number of elements in K, which can be infinite, and tau, it is the first time after S where we have at least two functions in this intersection. The pair Sx is called the bifurcation point if tau Sx is equal to S. It means immediately after time S, we have a possibility to get two different limit points. Now, before this time tau, actually, we have a flow property. It means that if there are no bifurcation points, then we get a flow. If there are, we can modify a flow in the following way. So fix some closed set that contains a set of bifurcation points and denote by sigma the heating time of this set F. Then we can define mappings psi as follows. Before time sigma, it coincides with theta, and after time sigma, we just impose the flow property. Again, psi preserves the trajectories of the skeleton, and this is my last result, that if the following condition holds, which means that if after time when the flow hits the set F, if it hits it again, then it coincides with the skeleton. So this is like a relaxation of the instantaneous coalescence property. Then we get a flow of mappings. And this result can be applied, for example, for the Tanaka SDE, where we don't have instantaneous coalescence property, but we still have a flow of mappings.
Georgii, I have to interrupt you.
I'm finished. Thank you for the attention.